Hi, it's Krste here. I'm excited to be giving a keynote at the summit, even if we can't all be together in person this year for obvious reasons. So the keynote today is entitled RISC-V, the next 10 years. So let's take a look and see what's going to happen, try and predict what will happen to RISC-V in the next 10 years. First thing to note is that general purpose ISAs do last for decades. So if you go back and look at the original instruction set architecture, the IBM 360, it's now 56 years old. That's kind of incredible. Intel x86 is now 42 years old. ARM is 35 years old, and RISC-V even is already 10 years old. So these are not only been around for a long time, but they're still in active development. By that I mean people are building new hardware implementations in advanced technologies that are based around these instruction sets. So they're alive in very active development, even though they've been around for decades. So these general purpose instruction sets do last for decades, and we hope RISC-V will last for many decades more. What's interesting, as I was putting this keynote together, I was thinking about special purpose instruction sets and how they don't seem to have that same property. So special purpose instruction sets do seem to come and go. So array processors, network processors, image processors, DSPs, GPUs, AI accelerators. Now, what's interesting is the types of processor tend to persist, but it's rare for the actual hardware instruction set to last more than a decade or so in each of these areas. And there's multiple reasons for that. One is just that naturally things that are specialized try to take the best advantage of technology at a time. And when technology moves along, the instruction set doesn't really scale to the newer technology. Another thing is in some areas, the general purpose processors catch up and there's less of a need, or they add extensions that capture the optimizations these special purpose ISAs would bring. But it's kind of interesting that these specialized processors don't tend to last for, the hardware ISAs don't tend to last for a long time, even if the type of processor does keep going. One other thing to look at is just what happened in the last 10 years. And I think from an architecture perspective, it's interesting to look back and just see how much actually happened. I think it's very easy to think things move slowly until you look back and then you see how much has really happened in a relatively short amount of time. For example, deep learning wasn't a thing 10 years ago. It's hard to believe given how dominant this topic is across the whole industry, hardware and software applications, that it just wasn't a thing 10 years ago. So, probably the thing that was really the breakout paper for deep learning was the AlexNet paper that came out in 2012. That's way less than 10 years ago. Another area that's sort of more frightening is whole new classes of security challenge appeared. It was only a few years ago that Meltdown and Spectre burst onto the scene. And both these topics are new in the last 10 years, and these are really now the primary topics of research in the architecture community. So things change pretty fast. And one of the fun things about computer architecture, why I like it so much, is that there's always new things to look at, and there's always new designs to do, and there's always new topics. And it's always right at the center of the computing industry. So looking ahead to the next 10 years, well, some predictions I can make that are pretty easy to make are that there will be new security threats, but I don't know what they'll be. Another pretty safe prediction to make is that there'll probably be some new application areas, but we don't know what those will be either. And another prediction I will make, this may be a little less clear, is that I think we will need to start on the RISC-V 128-bit address space definition in the next decade. I think if I remember back to the early 90s, I remember when MIPS came out with the R4000 with a 64-bit address space. And at that time, people were thinking, well, it's going to be a long time before we need 64 bits. But the smarter people had realized, there was this continuing growth in storage capacity, and it takes a long time to bring up new compilers, tools, operating systems to handle a wider address space. So MIPS kind of got ahead of the curve in putting out 64-bit at that time. And if you look now, people have 64-bit processors in their wristwatches. Okay, so I think this decade, we're going to see 128-bit become, we have to start working on it because it's going to involve quite major changes in all the tool chain, much more so than the 32 to 64-bit transition involved. And so I think we're going to see some serious work towards the end of the decade in bringing up 128-bit address spaces. They may not work the same as the 32 to 64-bit, who knows, but I'm pretty sure we're going to need more than 64 bits of address space. Thankfully, we've at least thought of that in RISC-V, and so we have a place to start, but it's going to take a lot of work to bring that up. So another prediction I can make safely for the next 10 years is that RISC-V is going to increase adoption throughout all the computing. I think the double whammy here is it's a free and open architecture, so anybody can adopt it freely. Everybody gets a free architecture license. But also we tried to make it a simple and modular design so it can adapt to these challenges, new application areas, new security challenges. The simplicity helps there, the modularity helps in adding things. So I think these are reasons why I think it's natural to predict that RISC-V is just going to keep increasing adoption. There's going to be new specialized processors. There always has been, there always will be. There'll be new ones. But I think the change will be that given the way things are going, they'll be more based on RISC-V rather than specialized and proprietary bases. One of the reasons there were a lot of different ISAs for specialized processors is there was not a free and open standard one people could easily use that made a good base for these specialized processors. But now with RISC-V, there's something that's designed to be, can be pared down to be very simple to act as the base of a custom accelerator. And so I think we're going to see more specialized processors based on RISC-V rather than on some other base ISA. These are kind of easy predictions for the next 10 years. So talking about RISC-V adoption, the reason I'm so gung-ho that it will be adopted more and more throughout computing is just the tremendous momentum we have right now. And so Aman's goal that we set a long time ago was that we would just become the industry standard ISA for all computing devices. And originally that was really just almost a joke that, yes, of course we will, but it's become true. And it's really happening. And we see this is happening much faster in more domains than anybody ever predicted. And there's demand for every performance level from very low to ludicrous, I like to say. And there's demand for basically every feature of every ISA ever built. So everybody wants to use RISC-V everywhere. And so there's tremendous demand to use it. And I think what's interesting with RISC-V is we're trying to do all this with a new model, which is a community developed instruction set specification. And so obviously there's been a lot of challenges just in how to do that with a community versus the standard model of a single company owning and driving the development of the ISA. So just to recap on how we run RISC-V, how does the ecosystem work? So at the center of the ecosystem, you have the RISC-V International. So RISC-V International is really an open standards body that manages the ISA specification. And the main product from RISC-V International is the specification itself, the go-to model and compliance suites. And this specification for the ISA, that provides the standard that's the interface between software and hardware. And so the RISC-V ecosystem is built around this ISA that lives in the middle. So the nice thing about having an open specification is that it enables open source cores to exist. And we've seen a great proliferation of open source cores. Again, all corners of the planet producing RISC-V cores, students, high school students even making their own RISC-V cores. Anybody can build these, and it's become a standard project for people to do. And there's more and more capable cores being available, some being used in commercial products. But RISC-V is not only about open source cores. There's also a large number of commercially supported cores as well, from a growing number of providers. And in fact, and all around the world again. And in fact, already RISC-V has more commercial core IP providers than any other instruction set in history. And as well as open source cores or commercial cores, because everybody gets an architectural license and can build their own core, companies are building their own RISC-V cores to use internally. For example, NVIDIA is shipping all their GPUs now with RISC-V on there as controllers. So many providers of RISC-V implementations, many places to do this, and many people providing compatible standard hardware. And to run on that hardware, you need software. And so really the crown jewel of RISC-V is the software ecosystem that's building up around the standard interface. And that software ecosystem includes both the open source community that has wholeheartedly embraced RISC-V. So upstream projects from GCC, Linux, BSD, a whole range of upstream projects are now embraced RISC-V as a mainstream supported architecture. But again, it's not only about open source software, there's also commercial software. So there's a large number of companies who are supporting RISC-V commercially, both with their own products and also supporting, providing support for the open source software for RISC-V. So this is the RISC-V ecosystem. It's big and growing. It's very vibrant, a lot of activity. And this is how we organize it. So a standard in the middle, an open standard in the middle, and then both open source and commercial hardware and software. Now, with such a big community, one of the challenges we have is in managing diversity at RISC-V International. So, one thing is people want to use RISC-V everywhere, and a single fixed ISA spec cannot possibly work for all domains. And we envisaged this when we designed RISC-V, so it was designed to be modular. We have different base ISAs for 32-bit, 64-bit, 120-bit address space. We have a set of different standard extensions that are optional, everything from single, double precision floating point, and an increasing set of optional standard extensions. And then we leave aside some space for vendors to add their own custom extensions. So projects, commercial providers can add their own custom extensions that are not managed in any way by the central organization. And the idea is you can combine these modules to build your own application-specific instruction set. So that's great. You have the flexibility. The challenge is that across the software and toolchain ecosystem, it can be difficult to actually support any combination of all these pieces well. So, at some point it becomes a responsibility of the implementer to support the software, but they also want to draw upon as broad a range of support as they can from the standard ecosystem. A second aspect of managing development here is we have a very large community with a lot of interests. And it's been great to see all these good ideas, all the task groups started at the Foundation International, but it's really important for us to prioritize and finish things to make RISC-V successful. So that's been really a theme the last year or so is working on prioritizing and finishing things. So the Technical Steering Committee in the new organization has been trying to focus the short-term effort we have on trying to meet the needs of at least a few application domains completely. And so looking at what are the gaps in the RISC-V ISA that means they cannot be used in these domains, or as well, what are the opportunities? What are things that would really enable RISC-V to take a lead in these different application domains? And so really what is needed for a complete and compelling solution to some of these application domains? Now, one of the ways we're structuring this focus is around the idea of architecture profiles. So profiles are something we've talked about a lot at the Foundation and RISC-V International the last 5 years or so, but it's really kind of crystallizing now that what we really are talking about are architecture profiles, and we've been coming up with a naming strategy for these. And so the two initial architecture profiles will be RVA19 and RVM19, and that represents the application processor profile for year 2019 and the microcontroller profile for 2019. And the idea of these profiles only include ratified extensions at the date of their creation of the profile. And each profile specifies the mandatory base and extensions needed to meet that profile, as well as what are optional extensions within that profile, as well as what standard extensions are not actually considered supported within that profile. So that the idea here is you want to reduce complexity for the software ecosystem and RISC-V users by giving a sort of more understandable synopsis of what's in a given core or a given hardware platform. And so the idea is that the mandatory base extensions have to be present in all the implementations. There can be some optional standard extensions, but also there are some extensions that we're not expecting to support. And so this kind of simplifies life for the software ecosystem, knowing that these things are not meant to be combined in say an application processor or in a microcontroller processor. And so the Technical Steering Committee at RISC-V is going to be deriving this future roadmap for the future architecture profiles. And our plan is to do the next one. So I should say the RVA19 are supposed to be built on the existing things already ratified. And we want to go back and retrofit these, and these are still in development, and release those so we have a very clear model of what's in a standard RISC-V microcontroller, for example, for 2019. But we're going to drive forward to add new features, new capabilities. And the next target is by next summit to have RVA21 and RVM21 developed for the next summit. So you'll be hearing a lot more about these architecture profiles from the RISC-V International. One other thing to clarify, profiles versus platforms. The architecture profiles standardize the ISA components visible to software, and that's both privileged and unprivileged components. Whereas platform standards really are more about the set of hardware implementation choices, a broader range of things, including the supported ISA, but including things like how a system boots, how its memory is configured, what are allowable memory configurations, how the system does discovery, device handling, debug, and attach, etc. So they're kind of more about a given implementation, whereas the architecture profile is really about the software view of the instruction set on that system. So both of these are very important. We'll be developing both of these to help bring the community together around some common standards. Another thing that will follow is a focus on verticals in industry. So the architecture profile is really a generic for a class of processor, but we also want to look at certain industry areas that may need additional specialized support. And so the technical steering committee is going to be prioritizing how we add extensions based on member interest. We cannot do everything all at once to high quality. And so the goal is to, amongst the membership, figure out what are the priorities and try and focus the group's efforts on getting those things defined and ready for commercial use. And this may involve enhancing the profiles or adding more profiles even to support different industry verticals. So this is another activity going on at RISC-V International. So just to summarize, there's a quick keynote. So next 10 years, there's going to be new application areas and there's going to be new demands for security dependability. And really, a free and open, simple modular ISA is really the best way of meeting these challenges. So that's why we believe RISC-V is going to be thrive in the next 10 years and be widely adopted. And we're trying to organize RISC-V International to help manage this upcoming complexity, as RISC-V is going to spread to lots more application areas, and we're going to have even more members and contributors. Just to like to thank everybody who's been helping out on the way so far. It's been great to see this community just really blossom and grow. Okay, that's all I have time for today. So I hope to see you soon in person sometime not too far away.